Line absorption spectrum. In this video we'll cover the line absorption spectrum. This diagram shows a couple of different spectrum. We've got the continuous spectrum that consists of every possible frequency of light, and what we're showing here is actually just the visible range, but it extends both to higher energy and lower energy levels. The bottom image here shows the emission spectrum. This particular case is hydrogen, where when the element is in a gaseous state at a higher energy level, the electrons return to the ground state and release photons. These photons are of very specific energy levels and are unique to the elements. Another spectrum, which is the one we're going to cover in this video, is the absorption spectrum. So in this case, when light of a continuous spectrum, so the top one, is incident on a gas, the frequencies that correspond to the energy levels in the atom are actually absorbed. And if they're absorbed, that light won't reach our eyes, which is why the absorption spectrum is a continuous spectrum with the black lines. And you can see that these black lines exactly match the change in energy level that's absorbed. This diagram just shows the two cases. The emission spectrum, so we've got a heated gas, and that heated gas produces discrete frequencies of photons and can be described with that image. Now the absorption spectrum has, for example, a white light. So in the visible range it has all the visible frequencies. The description here of high density hot matter suggests that in this case we might not only have just visible light, but a very large range of the continuous spectrum of electromagnetic waves. So this one would extend possibly to ultraviolet or further. And what that means is that when it's incident on a cold gas, those frequencies that perfectly correspond to the energy levels of the atom are removed from the continuous spectrum. So when a photon is incident upon an atom or the electron itself from the ground state, that photon is absorbed, and if it perfectly corresponds to the energy level there, it will go to that level. Since the electron is in the ground state most of the time, the photon that has to be incident on it has to be of the energy levels on the left here. Now for hydrogen, for example, the ones that we see in the visible light correspond to the energy levels that actually end in a second level. Now since the electrons in hydrogen are not at this level for long, the absorption spectrum of hydrogen in the visible range isn't really seen. In order to see the absorption spectrum for hydrogen in the visible range, the hydrogen atoms would have to be excited so the electrons are at this level, so the absorption spectrum can be seen. When we pass light that comes from the sun through a spectroscope and determine all the frequency of light that the sun consists of, we actually have a lot of the black lines that indicate absorption has occurred. Now these lines are called the Fraunhofer Lines. Rather than this being a continuous color spectrum in the visible range, you can see all the lines that are absorbed by our atmosphere. So simplifying the Fraunhofer lines in this diagram, what we've got here in the middle is the absorption spectrum of the sun. And here for iron, we've got the emission spectrum. And you can see that the emission spectrum for iron perfectly matches the absorption lines that are found in the sun. And what this suggests is that those energy photons that are emitted from the sun reach our atmosphere and are actually absorbed by the atmosphere and don't reach the Earth. And this suggests that the energy of the photon that's absorbed perfectly matches the energy level of an element that exists. For example, in those cases, it's iron. So this is again the absorption spectrum of the sun, however extended and split up all the way from the violet range in the visible light through to infrared. And you can see all the slight black spots that are absorbed and the elements that they correspond to. Explain the difference between incandescence and fluorescence.